What specific problem does the proposed method of infinite learning rate scheduling aim to solve in the context of continual pre-training of foundation models?
The proposed method of infinite learning rate scheduling aims to solve the problem of catastrophic forgetting and the limitations of traditional learning rate schedules, particularly in the context of continual pre-training of foundation models under distribution shifts. Traditional cosine annealing schedules assume a fixed training duration, which restricts the model's ability to adapt continuously to new datasets without significant forgetting. In contrast, the infinite learning rate schedule allows for flexible training without predetermined step counts, effectively maintaining model performance across diverse data distributions. Our experiments demonstrate that this approach not only enhances robustness to distribution shifts, but also outperforms repeated cosine schedules by eliminating the need for rewarming, which can destabilize training and exacerbate forgetting. Thus, the infinite learning rate scheduling provides a systematic solution for continual adaptation in self-supervised learning scenarios across both vision and language modalities.
How does the proposed infinite cosine learning rate schedule work? Illustrate its functionality step by step, including its phases and transitions.
The proposed infinite cosine learning rate schedule operates through a structured progression across 4 distinct phases. Initially, during the warm-up phase, the learning rate increases linearly from 0 to a maximum value, denoted as eta_max over a specified number of warm-up steps, n_w. Following this, the schedule transitions into a cosine cooldown phase, where the learning rate decreases according to a cosine function until it reaches a cooldown step, n_c. After the cooldown, the learning rate enters a stable constant phase, maintaining a constant value, eta_const, until reaching a decay step, n_d. Finally, the schedule concludes with an annealing phase, where the learning rate decreases exponentially until the end of the training task. This structured approach allows for continuous adaptation without the need to predefine the total training duration, effectively mitigating catastrophic forgetting during continual pre-training across diverse datasets.
Can you provide a simple example that showcases how the infinite cosine schedule operates during continual pre-training of a vision model on a dataset with significant distribution shifts?
The infinite cosine schedule operates through a structured 4-phase process during continual pre-training of a vision model, such as a vision transformer, VIT, on datasets with significant distribution shifts. For instance, when pre-training on a sequence of datasets like ImageNet, Places2, and FireRisk, the schedule begins with a warm-up phase where the learning rate increases linearly from 0 to a maximum value, eta_max. Following this, it transitions into a cosine cooldown phase until a specified point, n_c, where the learning rate is gradually reduced. After reaching the cooldown phase, the schedule maintains a constant learning rate, eta_const, until a decay phase begins, where the learning rate is exponentially decreased until the end of the task. This approach allows the model to adapt continuously to new data distributions without the need for rewarming, effectively mitigating catastrophic forgetting and enhancing performance across diverse tasks.
What are the key theoretical or practical advantages of using infinite learning rate schedules over traditional cosine annealing schedules in self-supervised continual learning?
The key theoretical and practical advantages of using infinite learning rate schedules over traditional cosine annealing schedules in self-supervised continual learning include enhanced robustness to distribution shifts and the elimination of the need to predefine training durations. Infinite learning rate schedules allow for continuous adaptation to new data without the risk of catastrophic forgetting, as they avoid the rewarming phase that can destabilize learning and degrade performance. In contrast, cosine annealing schedules require a fixed duration, which limits their applicability in scenarios with ongoing data influx. Our experiments demonstrate that infinite schedules maintain model performance across diverse data distributions, outperforming repeated cosine annealing in both average accuracy and backward transfer metrics. This flexibility and improved knowledge retention make infinite learning rate schedules a superior choice for continually pre-training foundation models in dynamic environments.
How was the proposed infinite cosine schedule validated? Please describe the experimental design, including datasets used and metrics for evaluation.
The proposed infinite cosine schedule was validated through a series of experiments across both vision and language domains, focusing on significant distribution shifts. For vision, the experiments utilized a small-scale masked autoencoders, MAE, pre-training on the CIFAR10 dataset, divided into 5 sequential tasks, and compared the infinite schedule against various continual learning CL baselines, including sequential fine-tuning and experience replay. In large-scale MAE pre-training, 3 datasets were employed, ImageNet Places 2 and FireRisk, which progressively introduced distribution shifts from object recognition to scene understanding and remote sensing. For language models, the datasets included DCLM baseline, Stack, and German, representing realistic distribution shifts. Evaluation metrics included average accuracy, forward transfer, FWT, and backward transfer, BWT, which were used to assess model performance across tasks, demonstrating that the infinite cosine schedule consistently outperformed the standard cosine schedule in both average accuracy and backward transfer.
What specific results were obtained from the comparisons made between the infinite learning rate schedule and the repeated cosine annealing method in your experiments? What do these results indicate about the effectiveness of your proposed method?
The experiments demonstrated that the infinite cosine schedule consistently outperformed the repeated cosine annealing method across various metrics, achieving higher average linear probe accuracy and backward transfer, BWT, in small-scale continual pre-training on CIFAR10. Specifically, the infinite schedule improved average accuracy by 1.87% and BWT by approximately 4% over the repeated cosine schedule without experience replay. Additionally, the infinite learning rate schedule effectively mitigated issues related to rewarming, which negatively impacted performance when using experience replay. In large-scale experiments, the infinite schedule maintained robustness to distribution shifts and eliminated the need for predefined training durations, indicating its superior adaptability for continual pre-training. Overall, these results suggest that the infinite cosine schedule is a more effective approach for continual learning, particularly in scenarios involving significant distribution shifts.